In this question, we are asked to find the percentage of oxygen-bound myoglobin under two different conditions of partial pressure. So for that, we will be using this equation here, in which PO2 is the partial pressure and P50 is a variable, which is given to us here as 10. So when the partial pressure is 1, we plug in 1 over, and then the P50, which in this case is 10, plus the partial pressure. And then when you calculate that, you get 0.09, which is 9%. And then we also calculate it at 100 to get the percentage of oxygen-bound myoglobin at that point as well, which we use the same formula. So in this case, the partial pressure is 100, and that is divided by the P50, which is given to us as 10, and the partial pressure, and then that is equal to 0.91, which is then 91%. And that is the percentage of oxygen-bound myoglobin under 1 partial pressure and under 100.
Perfect. Okay, so we're going to use this equation in order to find the P50 for the mutant myoglobin, which is just when 50% of the myoglobin has oxygen bound to it. The known values are the partial pressure of the oxygen and the percent that's already bound, which in this case we're going to have it as 0.2 for it to work in the equation. So we're going to set 0.2 equals 20 over 20 plus P50, and then we are going to distribute to cancel out our our numbers. So then we get 4 plus P50 times 0.2 equals to 20. Then we're going to get 16, and then the P50 divided times 0.2, we want to separate that, so we're going to divide, and then we get P50 is equal to 80 millimeters of mercury.
So I have the third question. It states, which one binds tighter, the wild-type myoglobin or the mutant myoglobin? And to start off this question, I did 1 and 2. So for the first one, I used the equation YO2 equals PO2, or partial oxygen, divided by P50 plus partial oxygen. And I got that the P50 for the wild type was 10 millimeters mercury. And I did question 2, which again using the same equation, but I filled in X for P50 since that was not given to us. And I got the P50 equals to 80 millimeters mercury. And so since 10 millimeters mercury is lesser than 80 millimeters mercury, that means that the wild type is better than the mutant myoglobin because it has a smaller P50. And having a smaller P50 means that oxygen can bind stronger to the myoglobin.
Okay, write the mathematical description of hemoglobin binding to oxygen and point out it indicates it has cooperative binding. So this equation would actually be the Hill equation, which is theta equals to the ligand concentration to the Hill coefficient over the dissociated constant plus the concentration of the ligand raised to the Hill coefficient again. But this is also equal to the saturation of, YO2, which is also equal to the partial pressure oxygen raised to the Hill coefficient over P50 plus PO2, which is raised to the Hill coefficient. So what we need to know is that the Hill coefficients are all the ones that indicates that hemoglobin has cooperative binding, and the higher it gets, the stronger affinity it has for oxygen.
Okay, question 5 has 2 parts. The first part asks, when oxygen molecules bind to myoglobin, will it enhance the interaction between the heme group and the protein? The answer is yes. When oxygen molecules bind to the iron atom in the heme group, the distal histine will stabilize the oxygen with hydrogen bonds, so that does enhance the interaction between the heme group and the protein. So the second part asks, why does myoglobin not have allosteric transitions? So allosteric transitions are when binding a molecule like oxygen at one subunit will change the conformation of the subunit, which causes adjacent subunits in the same molecules to also transition. So one example of that is in hemoglobin, where binding of oxygen changes the additional subunits to go towards the R state, which is the oxygen binding state. This doesn't happen in myoglobin because myoglobin is a monomer, which means it only has one amino acid side chain, so it doesn't have any additional adjacent subunits to change.